Probably the only person watching.
I just have to get it.
Альберт Соломонович, are you?
Let me start.
Yes, let us start.
Okay. So what I will talk about is an attempt to understand quantum theory and possible generalization of it. So I will start with some very general remark. So really, not only physics, but also other branches of sciences, they are based on the idea that you can predict the future. If you know everything at some moment, then we can predict the state in the next moments. So really, I'm stressing that you should know everything. So you should know the state of the system. And then in classical mechanics and in quantum mechanics, you can solve the equation of motion if you know the Hamiltonian classical and quantum mechanics. Find the state in all moments. The operator that produces the state in the moment capital T from the state at the moments little t is called evolution operator, and the possibility to find this operator is called deterministic. It means that your theory is deterministic. And quantum mechanics is deterministic in this sense. The probability in the usual understanding of quantum mechanics, they appear in the process of measurement, not in the process of evolution of state. So what I'm advocating today is geometric approach, where the starting point of the theory is a set of states. And what I will try to say is that if you know the set of states, then basically you can say a lot. You can restrict the evolution operator. You can generalize everything that happens in quantum mechanics. So my talk is based on a series of my papers. Some of them are very recent, and one of them is really very old. It was written in 1967. This was the first paper in physics that I had written. And it's called New Formulation of Quantum Mechanics. And in this paper, I analyze the dynamics of state, I introduce the set of states in the case when the algebra of observables is Weil-Clifford algebra, and analyze the evolution operators and so on in this setting. This paper was forgotten for many years, but this topic wasn't quite forgotten because a little bit later, the results of this paper were rediscovered in, I would say, in Western America by Umezawa, who gave the name thermofield dynamics, or TFD, to his approach. So also one should say this, in many cases, this approach based on L functionals introduced in my paper is equivalent to what is called Keldysh formalism or Schwinger-Keldysh formalism in statistical physics. Later I came back to the stuff in 2019. Let me say a couple of words about the basics of this approach in more detail. First of all, this set of states in definite moment, it is denoted by curly C with index 0, is assumed to be a convex set. And the reason is that I require that the set contains also mixtures of states. If you have several states, you can take them with different probabilities, and this will be a mixed state. The notion of mixture of states is really very, very general. And for example, in economics, it appears as a notion of mixed strategies. So the extreme points of the set of states, of convex set of states, are called pure states. Extreme point is the point that cannot be represented in non-trivial way as a mixture of other states. And together with the set of states, it is convenient to consider a convex cone consisting of non-normalized states. This is the set of points on rays that contain one of normalized states. So what can be done in this approach? First of all, you can prove an analog of the coherence in quantum mechanics and use it to derive formulas for probabilities that generalize the formulas for probabilities in quantum mechanics. I will not discuss this derivation in detail in this talk. I will give another talk for mathematicians in less than 2 weeks on 30th of November for Moscow Mathematical Society. And there this will be discussed in detail. Probably the most interesting point of this present talk is the statement that any theory can be obtained from classical theory with a restricted set of observables. This will be discussed in details, and I will describe the models that can be obtained from classical models in some detail. So the next thing that I would like to discuss is the following. So it is what I will say today is that yes, you can do many general things in the setting of geometric approach. But the only thing that I will not touch today is concrete calculations. However, I would like to say that these calculations in terms of L functionals, they can be identified with calculations in terms of field dynamics and Keldysh formalisms. And the calculations are not harder than in any other approach. Sometimes they are easier. Also, I would like to explain that functional integrals also can be derived in geometric approach. The next thing to discuss is the notion of scattering in geometric approach. To discuss scattering, you need translation symmetry, and then you can define particles and quasi-particles as elementary excitation of translation invariant stationary state. So if you have translation symmetry, you can consider scattering theory in geometric approach, but you cannot consider the standard scattering matrix. The right object is what I'm calling inclusive scattering matrix. That is related, its matrix elements are related with inclusive cross-sections. And what I will explain that this inclusive scattering matrix and inclusive cross-sections can be calculated in terms of generalized green functions. You can prove formulas that are very similar to the standard Lemon semantic Zimmermann formulas. So, as I have said that in this geometric approach, you can start with convex sets or convex cones. There is a theory of homogeneous cones that was developed mostly by Weinberg, and it is very natural to consider homogeneous cones in my approach. The homogeneous cones are also closely related to Jordan algebras. And really, the algebraic approach based on Jordan algebras is close again to the geometric approach. However, in this talk, I will not talk about homogeneous cones and Jordan algebras. This also will be delayed for the talk on the end of November for mathematicians. And the last thing that I would like to mention this introductory part is some work in progress that is listed on this slide. I do not think that I have time to talk this in some detail. So, after this long introduction, I would like to start with some precise statement. So we are starting with a bounded convex set, which is a subset of some Banach space, or more general, some topological linear space. I assume that this set is bounded. This happens in quantum mechanics and classical mechanics, and really it leaves some important restrictions on the theory. So now I will consider the evolution operators. And the evolution operator should transform a state into state. So it should transform my convex set into itself by means of invertible transformation. So the evolution operator should belong to the automorphism group of my set of states. However, in some series, you should impose some restrictions on this evolution operator. You should fix some subgroup of the automorphism group that I denoted by curly V. And observables are pairs of the capital A and small a, where A belongs to the algebra of this subgroup, and A is a linear functional which is invariant with respect to A. So really, in infinite dimensional case, there are some difficulties in definition of the algebra. I will disregard these problems. Formally, you can say that A belongs to this Lie of curly V if you can consider the exponent e to the at, and this exponent belongs to subgroup denoted by curly V. So these are the basic objects of geometric approach. So you can write down the equations of motion. This sigma is evolution operator. The derivative of sigma with respect to t is equal to h of t composed with sigma of t. You can consider this formula as a definition of h of t, which I call Hamiltonian in quotation marks. So that's this definition of Hamiltonian. From this definition follows that h of t belongs to the algebra of curly V. However, usually we go in opposite direction. We think that we know this h of t, and we are trying to solve the equations of motion to find the evolution operator. And I can illustrate all the stuff on standard quantum mechanics, where the set of states consists of all density matrices, and this curly V consists of all unitary operators acting on in natural way on density matrices. The equations of motion, standard equation of motion, where you have commutator of density matrix in some self-adjoint operator, which is a Hamiltonian without quotation marks, and this Hamiltonian in quotation marks is the commutator, this standard Hamiltonian denoted by H hat. So this observables are commutators with self-adjoint operators up to a factor of I, and this linear functional is trace of A hat multiplied by K. So now, let me explain how to calculate the probabilities in this geometric approach. The prescription is as follows. You should define a projection denoted here by P, that is defined in the terms of evolution operator. In terms of, you should take the average of evolution operator for time t, and you take this capital T tending to infinity. If A is diagonalizable, then this projection operator, it is easy to check, it sends all eigenvectors with non-zero eigenvalues to 0, and it sends the eigenvectors, the zero modes, it doesn't leaves them intact, it doesn't change them. So what happens in standard quantum mechanics? If you take A hat representation, where the operator A hat is diagonal, then this projection operator sends every density matrix into its diagonal part, and under the assumption that A hat has simple spectrum. So this is precisely what happens in standard quantum mechanical decoherence. And to calculate the probabilities, you should really represent this projection P of X as a mixture of pure zero modes of A. So you will get standard description of probabilities, but only in the case when A has simple spectrum. If the spectrum is not simple, you should modify this picture a little bit. So you should introduce the notion of robust zero mode. the zero mode of A is robust. If changing a little bit, you still have a zero mode of changed operator that is close to original zero mode. And the right way to calculate probabilities is to, instead of operator P, that is a projection on all zero modes, you should take projection on robust zero modes and represent the projection of X as a mixture of pure robust zero modes. And this prescription definitely coincides with standard prescription of standard quantum mechanics. But also it can be derived from the coherence that I promised this derivation in my talk from to give this derivation from in my talk from mathematicians. So now I would like to go to my next topic. This is the statement that you can get standard quantum mechanics and generalization of quantum mechanics from classical mechanics with restricted set of observables. Let me start with some Poisson manifold that I denoted by M. Poisson manifold is it's a manifold where you have a notion of Poisson bracket. So it's a very symplectic manifold. It's a Poisson manifold. Space of smooth functions on Poisson manifold is a Lie algebra with respect to Poisson bracket. These smooth functions on M are classical observables. But we consider not all of them. We consider only a part of them. We consider a Lie subalgebra of this algebra of all smooth functions. And every function generates a vector field, Hamiltonian vector field on Poisson manifold M. So I define the elements of this Lie algebra denoted by Gothic G by H sub X, where X is, stands for vector field with Hamiltonian H sub X. And then one can define what is called the moment map, denoted by mu, from Poisson manifold for G dual that is, and this map, this is standard definition, is it is given by the formula in the last line. So, and now, what I've considered two classical states. Classical states are simply probability distributions on M. And I say that they are equivalent if the formula 1 is valid for every x in my algebra Gothic G. So what does it mean? This is precisely means that two states are equivalent if calculations with these states lead to the same results for every Hamiltonian H sub x. So I define a map new. Go back to this definition. The sense all probability distributions on M or classical states to some points of G dual. This is what I'm formula here is the obvious definition of the map probability distribution to a point of G star. This is basically the extension of moment map for probability distributions from standard from pure states, which are points of Poisson manifold, to mixed states that are probability distributions. So what is easy to prove is that two states, rho and rho prime, are equivalent in the sense that I have explained if the map nu sends them to the same point of G star. And the proof is written on this slide. It is basically, you should take the definition of moment map and to look at the right-hand side, you will see that the right-hand sides coincide. This is precisely means that rho and rho prime are equivalent. But this means also that nu of rho is equal to nu of rho prime. So basically what did we do? We took the classical theory with Hamiltonian restricted to some set that Hamiltonian are denoted that I consider denoted by H sub x, but there are other Hamiltonians also. And I considered space of states that are equivalent in the sense that I have explained. States that are, if you have equivalent states, I'm saying that there are redundant states, and I eliminate the redundant states. And what I have said is that elimination of this redundant states gives me the set that I denoted by N, which is obtained as a convex envelope of the image of the moment map. The evolution of classical states agrees with evolution of quantum states. And so you can start here with any Poisson manifolds and any subgroup of its group of functions with respect to Poisson bracket. And so you have possibility to prescribe, to construct physical theory with any prescribed symmetry group. Or you can get a supergroup here, because all of the stuff can be applied also to supermanifolds. So this construction can be applied to many cases. In particular, it can be applied to complex projective space, which is symplectic homogeneous U manifold, where U stands for unitary group. And look what happens there. The moment map on projective space maps this points of projective space into the pure states. So this precisely pure states in classical, in quantum mechanics, standard quantum mechanics, are points of projections of complex projective space. There are points of Hilbert space that are defined up to a factor, up to a numerical factor, but this is precisely projective space. So when you take this convex envelope, this means the smallest convex set containing all this stuff, you get precisely density matrices, because density matrix is a mixture of pure states. But pure states are precisely in the image of moment map. So basically, what did we get? Is that we can get a Hamiltonian, the standard quantum mechanics, if you take a projective space, complex projective space, and identify all equivalent sets that we can say that we eliminate redundant states, and this leads you to standard quantum mechanics. But what I am saying, that you can do the same stuff with any Poisson manifold, and you will get a plethora of other theories that maybe have some physical meaning, maybe they do not have any physical meaning. But then, so you can say that you get here some physical subseries that are looking for physical interpretation. Usually in physics, we work in different setting. Usually we have some physical system, and we are looking for equation that describe this physical system. So that this is the way from physics to equations. But I would like to mention that at least in two cases, physics went in different direction. Remember that Yang-Mills series were invented without any explanation of physical meaning of non-abelian Yang-Mills. It took, I believe, about 13 years to get a real physical interpretation of that. And the same knowledge, the same stuff happened with string theory that was invented for strong interactions, but now we think that it should be applied in completely different setting.
Oh, Альберт Соломонович, I'm sorry. May I interrupt you and just ask because I'm thinking.
Sorry?
Lost. May I interrupt you and ask a question about probably?
Yeah.
Can you explain just in simple words what you will get from this construction for like finite dimensional CP complex manifold projective space?
But by finite dimensional, it is not finite dimensional. I didn't say it.
Didn't say it?
This is a complex projective space that I take as symplectic homogeneous manifold. It's infinite dimensional complex projective space.
Mm-hmm.
In all of my calculations, I did not say that Poisson manifold is finite dimensional.
Mm-hmm.
Can be infinite dimensional as well.
And can it be can we compare it to some physical theory we know? Like, is there any, just to check to compare our maps, because I mean, how you're saying it's very mathematical, and it's kind of what type of, I don't know, what type of theory or what class of theories we should expect from this approach.
So
like, just to compare with standard, I don't know, Lagrangian approach, for example.
So really, what we know now is what happens when you take complex projective space. Then you get the standard quantum mechanics, period.
Yeah, but quantum mechanics is, I mean, quantum. What do you mean standard quantum mechanics? Just
it means that standard quantum mechanics starts with Hilbert space.
I mean,
Start with Hilbert space, and the dynamics is described by self-adjoint operators.
All of them. You mean that kind of action is not specified? You just consider a very general thing without specifying.
It's a completely general thing. You can take any Hamiltonian, any self-adjoint, any quantum mechanical model, any can be obtained from complex projective space.
Yeah, but I'm asking just, I'm sorry, I'm confused. But if I want just concrete theory, what should I do?
So you should specify your Hilbert space. Your Hilbert spaces, all of them are isomorphic. But nevertheless, they are different. You should take probably square integral functions of some space. And after that, you should choose something as your Hamiltonian. That's something you should take self-adjoint operator that specifies the dynamics. So that's this is standard. What I am saying, what you are doing in standard quantum mechanics. You take Hilbert space. You choose the Hamiltonian. So that's so what I am saying, that all this stuff, everything now can be obtained from classical mechanics on projective space if you restrict your set of observables. And so really this is I believe this philosophically, this is a very important statement. Basically, this one possible explanation of the origin of quantum mechanics. You have classical theory on complex projective space, but you restricted your observables to some definite set. And after that, you are saying then you should eliminate the redundant states, and you will get standard quantum mechanics. But maybe the situation physically is a little bit different. Maybe you have this special Hamiltonians that you only consider. These are Hamiltonians that are generators of unitary group. But maybe you have something else. You simply, maybe your devices are not good enough to specify this other possible Hamiltonian observables, but they still exist. And this was precisely, this leads to some deformation of quantum mechanics. And in this case, you will get what is called nonlinear quantum mechanics by Weinberg. So basically, what I'm saying, that this nonlinear quantum mechanics by Weinberg, suggested by Weinberg, simply means that you, in usual quantum mechanics, you have only some possible observables, and nonlinear quantum mechanics, you take all of them. So that's what happens when you're starting with complex projective space. But you can start with something else, and then it's completely ignorant. I do not know what will happen. I can predict what I can calculate. For example, I can calculate, can define equilibrium state, and I can calculate it. I can calculate correlation functions, but I completely, I do not, I'm completely agnostic. I do not know what physics in real world corresponds to this stuff, if it does correspond. I do not know.
But do you have Hilbert space, Hamiltonians, all that in this case? In this?
No, I do not have Hilbert space. But
You don't have Hilbert space. But
I have to say, so really, Hilbert space is really only some device to define a complex projective space.
so so this is the property of the complex projective space. But if you take another space that you're saying that the language of Hilbert space is kind of misleading. It's not appropriate in this case, right? That's what you're saying.
Problem, the language of Hilbert space is a wrong language by many reasons. So really, basically, this when you are working, for example, with CCR, this canonical commutation relations, or with Weil algebra in different terminology, Then you have many Hilbert spaces, many representations of CCR, and the invention of L functionals was based on the idea that you should not work with many Hilbert spaces. You should work with L functionals that combine all of these Hilbert spaces together. So that's all the stuff is also very clear in algebraic approach to quantum field theory. More questions?
Yeah.
Excuse me.
So, yes, Misha, please.
If it is a so general construction, then obviously you can explain it on a simple example. For example, a spin 1/2 in magnetic field or something like that. So what is the complex projective space in this case, and so on?
Oh yeah, of course. I can explain this, but more or less. So look. When you have the spin 1/2 situation, then the situation is very, very simple. Your Hilbert space is two-dimensional, and complex two-dimensional space, and this complex projective space is one-dimensional. So basically, it can be identified with Riemann sphere. So that's it is. And by the way, in this case, it's really this interpretation in terms of projective spaces is really quite useful. Basically, many people work in this case in such situation. But basically, when you are working with Hilbert space, you are always working with projective space, because what is projective space? Projective space, you should take a linear space, you should delete 0, and you should identify the points of linear space that are proportional. But this is precisely what you are doing in quantum mechanics. You are working with complex projective space without saying this. But you are doing this.
And what is the corresponding classical system which describes this spin system?
The classical system is as follows. You have projective space. On this projective space, you have an action of unitary group. And therefore, you have corresponding infinitesimal generators that correspond to self-adjoint operators. Basically, self-adjoint or skew-adjoint operators, to be more precise in mathematical language. And this is only factor of I. So really, your Hamiltonian of my set H sub x is simply self-adjoint operator. That's it. In this case, everything is completely standard. More questions? So I will go ahead. So here, as I said, you are what did they invent is a lot of theories that may be related to physics in some way, maybe not. This is standard, again, this is a standard situation. You can write down any Hamiltonian in standard quantum mechanics. It could be related to physics. It could be completely meaningless from physical viewpoint. But from mathematical viewpoint, it's completely reasonable to consider any Hamiltonian. So I finish at this point with stuff of restricted set of symmetries, but I should go to calculations in my setting. What I would like to explain, then in this setting, I can also introduce the techniques of functional integrals. And basically, this can be done by means of techniques of symbols that was invented by Beresin. So what I am saying, the symbol of operator is a function that depends linearly of it. And so that I'm saying that operation of symbols on symbols denoted by star corresponds to multiplication of operators. And then a very simple consideration can be used to calculate the symbol of evolution operator in terms of some operations on symbols of Hamiltonians. And in many cases, this leads to functional integral. So I'm concerned, probably I have no time to consider a little bit more specific situation, but the only thing that I would like to say that, for example, for L functionals, you can write down the functional integrals and use them. The next thing that I would like to consider is the notion of scattering, the notion of particle, the notion of scattering. To define scattering, you need not only Hamiltonian, but also momentum. You need not only time translation, but also spatial translations. And basically, what does it mean? So if you have a theory, then you can consider symmetries of this theory. As always, symmetries are something that commutes with evolution. And I consider the case when you have translation symmetry, that together with translation in time direction form a commutative group. So, and if you know this commutative group, you can try to define particles and quasi-particles. So the particles are defined as elementary excitation of ground state, and quasi-particles as elementary excitation of any translation variant stationary state. For example, you can take equilibrium state. What happens here? In algebraic approach, you have translation symmetry and the kind of asymptotic commutativity. You can define scattering matrix. But in geometric approach, it seems that it's impossible to define a scattering matrix. But you can define what I'm calling inclusive scattering matrix. Scattering matrix is related to inclusive cross-section. So I remind that inclusive cross-section is something that appears when you consider some scattering process without looking at all products of scattering, but only at some of them. So you're summing over all processes, which gives you particles that you do not want to take out. And usually in real experiments, you see inclusive cross-sections, not standard cross-section. So I will explain how to define generalized green functions. And the main statement is that inclusive scattering matrix is generalized green functions on shell. Remember that usual scattering matrix is usual green function on shell by LSC. So here the same, basically very similar statement is proven for inclusive scattering matrix. But I should explain what is the notion of particle, or quasi-particle. I said that it's elementary excitation, but what is an elementary excitation? It's easier for me to start with Poincare invariant situation when you have Poincare group, a symmetry group. Then I define an elementary space in Poincare invariant theory, the space of irreducible unitary representation of Poincare group. Remember that in standard approach, you also starting with such irreducible unitary representation of Poincare group in relativistic theory. And a particle is specified by a map of this elementary space in the cone of non-normalized state that commutes with action of Poincare group. But you need something else. This map I denoted by sigma, and you need some linear operators corresponding to elements of this elementary space that get you this particle state from Poincare invariant state from vacuum state. But if you have the translations on the translation theory, you do not have Poincare symmetry. Then you also can define the notion of elementary space, as done in this slide. And basically, the space is the same as in Poincaré invariant case. However, the time translations are different. The spatial translations act precisely in the same ways in Poincaré invariant space. But time translation, they commute the spatial translations. And, this means that they can be defined as multiplication by exponent of some Hermitian matrix. And again, the elementary excitation is specified by a map of elementary space to the cone of states, which commutes the spatial and time translations. And again, we assume that there exists such operator L of phi that makes this sigma of phi from spatial, from the state omega, that is now only translation variant and stationary. I would like to stress that this map sigma is not a linear map. Usually it is quadratic or Hermitian. What I've written here is the definition of inclusive scattering matrix. What I've written here, some conditions that allow me to prove the existence of limits that define this inclusive scattering matrix. And I do not want to go in any detail in this slide. I simply do not have time for this. But what I would like to say now, I would like to explain the notion of generalized green function that can be defined in geometric approach, but in geometric approach this is not a simple problem. I will use algebraic approach to give this definition. In algebraic approach, the starting point is unity associative algebra with involution. And the state is defined as positive linear functional on this algebra. To develop scattering theory, we need time and spatial translations that can constitute a commutative group. And the standard definition of this time translation, if you have an element of associative algebra, and this algebra is called algebra for observables, you'd say that this is A of x and t, where x corresponds to spatial translation and t corresponds to time translation. Now, so for physicists, this A of x simply fields, but these fields are not non-local, not necessarily local. But what you need to define a scattering matrix you need some requirements of symptotic commutativity that I have written here in very thick form, but you need really more. So in this case, you can define green functions, taking as usual time-ordered product, chronological product. And the standard LAZ formula, it gives you the scattering matrix in terms of green function. However, you can consider also generalized green functions that are obtained if you take two factors. One of them chronologically ordered, times are decreasing, and another has anti-chronological times are increasing. And so you can define this generalized green functions in terms of these two factors, chronological and anti-chronological. And these generalized green functions, they appear very naturally in the formalism of L functions. They appear in Keldysh formalism. They appear in terms of field dynamics that I mentioned. And that there is a diagram techniques for calculations then. It can be very easily derived in formalism of L functions, but can be derived in any other formalism also. And the statement is that as I have said, you can get inclusive scattering matrix in taking these generalized green functions on a shell. So
probably missed the point. Why you calling them generalized?
If you take a green function, then you are taking chronological product.
Mm-hmm.
If you take, I do not know a good name for them. I call them green functions with double G.
Mm-hmm.
The first letters. It seems that in Keldysh formalism and in TFD, there is no special name for that.
Okay, but if we stay with just ordinary chronological ordering, then those just coincide with order. I mean, you said that there is a Feynman rules, Wick's theorem. You said that, right? So you can compute these functions by some kind of perturbation theory.
There is this more or less the rules are precisely the same.
Yeah, but what's the difference? Yeah, I probably want to understand what's the difference with standard approach. If you have like similar rules, what's kind of conceptual difference at this point?
Maybe let me answer your question in a couple of minutes.
All right, sorry. Mm-hmm.
So I would like to explain, it is very easy for me to explain the language of L functions. What is the L functional. So if, as I have said, L functionals are invented to take together all representations of CCR. So, and what is, if you have a representation CCR, you have a density matrix or any trace class operator, you can assign a function of alpha star and alpha. Operator, where alpha is a function of on this discrete set M, but you also can take K continuous and define L functionals by the same formula, taking integrals instead of sum. So what is important, that this expression always exists, because if this alpha is square integrable, because the operators that are written here are unitary, and they, by definitions, they are defined in CCR. So, and what do you get here? You have this, when you go to this L functions, you basically are doubling the number of variables. So this is something that happens also in Keldysh formalism, or also in TFD. Then what you are doing here, basically you can take all operators that act in CCR and transfer this to L functions. So really look what is written here. So basically you will get the action of two copies of algebra on L, because the density matrices can be multiplied by operators that I have denoted here by A and A plus. You can multiply them from the left and from the right. So everything is doubled here. So now I can say what happens with L functions, these green functions here. So basically, in L functions, you can consider the order, the standard time ordering, but it will be really both time ordering and anti-chronological ordering in standard situation, because when you multiply from the right, then using the language of L functions, then time ordering reverses. Basically, in the formalism of L functions, you consider more or less standard green functions. But because you have a doubling of the number of fields, you get more than standard green functions you get generalized in functions. So in the language of L functionals, you can consider the action of the evolution of state. So this what happens here is that you can start with Hamiltonian H hat in representation of CCR. And usually this Hamiltonian, if it is translation, it doesn't have any sense. But you can transfer it to L function. But you can get, you'll get two operators corresponding to one of Hamiltonian. One corresponds to multiplication from the left and another to multiplication to the right. It both appear in equation of motion for density metric. And what do you get? You get equation of for L functional, and this will be precisely the equation of the type that I consider it. This Hamiltonian in quotation marks. And so, and this this quotation marks Hamiltonian is difference of two parts. One of them I denoted by the same symbol, and another I denoted by H tilde. And again here, you have the equations of motion that do that cure the ultraviolet divergences. But if there are no ultraviolet divergences, still the equation of motions in Fock space are usually ill-defined because of trivial divergences with respect to integration over volume. So what do you have when you are working with L functionals? The techniques are precisely the same as the standard technique when we are working with CCR. The only difference, the representation of CCR is doubled, and there is no unitarity. But still you can do everything that you want to calculate the operator of evolution, to calculate green functions that become generalized green functions. And that's it. So what I'm saying now is that L functions are really a very good example of this geometric approach in some particular situation. But this approach can be generalized to many situations. In particular, it can be generalized to the case when you have spin operators. And it's my understanding that this generalization should work very well for spin glasses. It doesn't require the replica trick. Already there are papers where Keldysh formalism was applied to spin glasses without using the replica trick. But I believe that the formalism of L functions, the picture will be even simpler. You can use many other techniques in the formalism of L functionals and initializations. For example, you can use the techniques of perturbiners to calculate the three-level scattering inclusive scattering matrix. But I think that this is a time for me to finish my talk. Any questions?
May I ask you a question?
Yeah.
Okay. Альберт Соломонович, if somebody will ask a question, what is the difference between your approach and standard one? Is it okay to answer that in the standard, in your approach, you consider projective sets as the basic ones, and in the standard, it is Hilbert vector spaces, Hilbert vectors?
No, I do not think so. So that's first of all, for example, what is my approach? If you take the geometric approach, and still you are would like to work in Hilbert spaces, then you should not consider projective space. You should consider density matrices, all of them.
Yes.
Not only pure states that correspond to projective space. But also, what I go further than that, and in particular, if you have Hilbert space, you also, excuse me, if you have algebraic approach, then you work with algebra of observables. And again, usually people work an algebraic approach in Hilbert spaces that are representations of this algebra of observables. Again, I don't, but there is a definition of state, which is positive linear functional, not algebra of observables. And my approach doesn't require any Hilbert space. It requires this set, this convex set of linear functions in the algebra of observables. But again, this is not the end of the story for me, because my starting point is the set of states. This is the starting point, and observables are secondary. In this case of algebraic theory, the algebra observables is a primary notion, and it was understood already almost 90 years ago that this is the wrong thing. Instead of associative algebra of observables, you should consider Jordan algebra. It was suggested in the 30s of last century. So that's my approach is much more general than you think.
Well, thank you. Thank you.
Any other questions?
You considered the quantum mechanics to some extent as the classical mechanics supplemented with some constraint. Since in quantum mechanics we have Planck constant, the Planck constant should be introduced in this constraint. How it can be seen in your language. For instance, when you consider Mayal quantization of classical mechanics, the Planck constant enter their Mayal product of function on the phase space. And how the Planck constant enter your constraint?
This in very trivial way. Yeah. So really, okay. So that's you have. You can say that it doesn't enter at all. It enters in the choice of your operators. Basically, when you are working in Hilbert space, then also the Planck constant doesn't enter the general theory. Planck constant enters when you are writing your Hamiltonians, your momentum operator. There is a Planck constant there. But when you are considering quantum mechanics without specific choice of Hamiltonian, then the Planck constant is not there.
But why? So for instance, when you consider the Mayal formulation of quantum mechanics, you for a moment you can forget about Hamiltonian, but instead of you have functions on the phase space, algebra of functions on the phase space, but you modify the multiplication of function, and Planck constant enters the multiplication rule.
Yeah, but this is
without any Hamiltonian.
No, that's this is simply because you still did the task for Hamiltonian. When you are yes, of course, you can consider quantization, not only any quantization. And in this quantization, you can insert the Planck constant. Yeah. So if you would like to compare the standard quantum mechanics with classical mechanics, then definitely you need Planck constant. Because if you would like to compare your concrete theory, but not at the moment that I look at the stuff, because what I'm doing here, I consider complex projective space with action of unitary group. When you are looking at this infinitesimal operators of unitary group, you get self-adjoint operators, all of them. But when you are you would like to compare with something physical, then you should consider say momentum operator, putting Planck constant there. But this is not something that has an influence on my construction. My construction, I didn't choose any Hamiltonian, and therefore Planck constant doesn't appear.
Yes, Maxim has a question. Maxim.
Yeah.
Yes. So Альберт Соломонович, thank you for the talk. What is it somewhat related to the previous question? If you have a formulation of quantum mechanics in terms of deformation quantization, in terms of star product, you mentioned the statement that quantum system looks like a subsector of classical one. What does it mean in terms of respective algebras? Because, for instance, we know that evolution is governed by Liouville equation, which is in classical mechanics is in Poisson algebra for the probability density distribution, and in quantum mechanics for density metrics in the non-commutative algebra. How can one get into another? Maybe I missed something important.
Yeah, that's a good question. So really, yes, this is definitely true, that your equations of motion on classical space are Liouville equation. But remember that your space is really complex projective, infinite dimensional complex projective space. You have completely different infinite dimensional Liouville equation. You cannot compare it with, but when you quantize the theory, you take finite dimensional Liouville equation on usual Euclidean space, and you are going to quantum theory, introducing the Planck constant. But here, your Liouville equations come absolutely different. It is an infinite dimensional equation. And so that's, and it is equivalent to Schrödinger equation precisely, to equation of motion quantum mechanics precisely. If you in quantum mechanics, you have chosen the operator containing H bar, this Liouville equation will contain H bar. But nothing wrong with this. This is not the Liouville equation of standard classical mechanics on finite dimensional space.
Okay, thank you.
More questions? So okay, if there are no more questions, that I would like to invite you for my talk on November 30 for Moscow Mathematical Society, where I will explain some stuff that I explained here, but also some stuff that wasn't explained in this talk. So,
okay. Thanks a lot, Альберт Соломонович.
Thank you.